Très
Yo,
bonjour, Ludo. Comment vas-tu?
très bien. Ah, on peut parler.
Oh oui, un peu. Oh, j'ai presque oublié mon français, mais un peu, ça marche.
Ah non, franchement, c'est très convaincant. Franchement, nickel.
Ah, c'est bien. À chaque matin, j'essaie d'écouter le radio, c'est la radio Canada. Et donc,
Mhm.
ça vient du Québec. Et puis, c'est les nouvelles ils touchent partout au monde, surtout en Ukraine maintenant, mais aussi il y a des nouvelles locales qui viennent du Canada francophone. Et donc, oui. Donc, je suis un peu bon, j'essaie d'utiliser ça pour maintenir mon français un peu.
Ah bah, tu parles du français du Québec?
Oui, ouais, oui, c'est le français de Québec, mais tout le monde me dit que je n'ai pas l'accent québécois. Donc,
Non,
c'est pas le cas.
non, non, franchement, tu peux aller à Paris, c'est bon, tu auras l'air parisien au milieu, tout ça. Non,
Ah, bah,
c'est
tu
très
vois,
bien.
ouais, bon, maintenant, ça fait longtemps, mais j'avais une copine qui était française, donc, ouais.
C'est
Elle
pour
n'était
ça.
pas, oui, elle n'était pas québécoise, elle était française. Euh,
Je
right,
pense que
okay.
Han comprend ce qu'on dit aussi, n'est-ce pas, Han?
Hi.
Are you
Ah,
guys
he's mieux.
speaking?
I was just checking your French.
Oh, are you guys speaking French?
Heard that.
Okay. Yeah.
Hi.
Hi.
Hi, Pengcheng.
No, so
Ludo, I made you. Go on.
how's Ukrainian different from Russian? Or is it different? I mean, I have no clue. You know.
They use similar alphabet. There are like 3 or 4 letters that are different, but otherwise similar. I'd
I
say
see.
like I think the analogy I gave is closer to between the analogy between Portuguese and Spanish.
Mm.
By the way, Ludo, you could try to share your screen in the meanwhile, in the sense that if it's written language, then both Portuguese can understand what's written in Spanish, at least the general meaning, and the other way around. But when it's spoken, especially fast, then it's not so easy, and it's also kind of asymmetric. It seems to be easier for Ukrainian people to understand Russian than the other way around.
I see.
But that's also true of Portuguese and Spanish. Like I was told that for Portuguese people, it's relatively easy to understand Spanish speaking, but the other way doesn't work for whatever reason.
That's interesting. Yeah.
Yeah, so that they're kind of sister languages because they all developed from the same family, but they kind of bifurcated from one another about 1,000 years ago. And so since then, they split. Ukrainian in some sense is closer to Polish, you could argue, in some words.
Mm. Very interesting.
And I can say that sometimes for Brazilians it's easier to understand Spanish than Portuguese, but that's a different term.
Right. Well, in case of Ukrainian, there is no Latin root, right? So it's all the words are totally strange, probably to any Western speaker.
Yeah.
Okay.
Yeah.
Interesting.
And I know, yeah. And good monde, that's Ukrainian, right?
Well, it's not exactly that, but so okay. Let me see if I can type it in chat. So it's spelled like this. Oh, autocorrect. Never mind. No, don't correct me, please. Okay. Sorry. Ignore the first one. So
Okay.
this is used when you say cheers, when you hold a glass, but it literally translates into like let us be, let us prosper, something along these lines. But I agree. But I agree that it sort of sounds like this, right? Did I write it correctly?
Yeah. Yes, exactly. Yeah.
Yeah. So the French bout du monde means what? The end of the world.
Yes.
Yes, that's not what the phrase means in Ukrainian. It just means cheers.
I see. Interesting.
All right, so I can see that the slides are shared. That's all good. Let us wait a couple more minutes. That's what we usually do in case more people want to join.
By the way, you can see my mouse moving, I guess.
Let me see.
Yeah.
Yes, perfect. Yeah, that's good.
And so generally, I mean, so for the second part of my talk, that's the first time I'm giving this talk, so I'm not completely sure how long it's going to be. It should be okay. But just to say that please feel free to interrupt me anytime if you have any questions. I mean, the usual thing. If you have questions or anything, I have planned to have enough time for questions. So please feel free to interrupt me if you want, if you need to.
Maybe Andrew, you can introduce a speaker.
Yeah. I think maybe now is a good time. So let's see. Let me see if the camera is rolling. Yes, it's recording. Ludo, I meant to ask you, okay with us recording your talk?
Yes. Yeah.
Very good. All right. Well, so I mean, maybe I should start. Okay, well, let me start from beginning of Ludo's career. So technically, he's a civil servant of the French Republic because he comes from one of this prestigious school, École Normale, in Lyon. And so after having done his was it undergrad or grad school? No, undergrad. He then did a PhD in the same school, correct?
Yes. Yeah.
Yeah, which is probably not uncommon in France. And then Ludo proceeded to do postdocs at Max Planck Institute in Dresden. And then became a group leader in Okinawa Institute of Science and Technology. And then since 2017, he moved to his current position, which is he's a researcher at the, oh gosh, how do you translate CNRS? Centre National de Recherche, right, so National Center for Scientific Research in France. And as you know, there's like a natural organization with multiple offices, a bit like Max Planck in Germany. So Ludovic is in Bordeaux. So I personally met Ludovic when I visited Okinawa one time. This was a long time ago, and that was very, very nice. And since then, Ludo has continued on his trajectory, looking at strongly frustrated spin systems, and in particular quantum spin ices. And today we're going to hear about interesting story of the four-dimensional emergence of magnetic monopoles. So Ludo, please go ahead. The floor is yours.
Thank you. Thank you very much, Andre, for the invitation for this seminar and for the very nice introduction. I'm very happy to be able to present to you our most recent research that we have been doing over the past year or so. So this seminar will be in two parts. The first part will be about electron. It's about two very recent preprints that we have submitted a couple of months ago. The first one was about electron holography and how we can use electron holography to try to see monopoles, magnetic monopoles in spin-ice systems. And the other one is about a new geometry of frustration, center power lattice, and the interesting physics that can emerge from that. So, yeah. So first, let me thank my my collaborators, so that you can see here. So it's a double project, so there are many people to thank. The first part about electron holography has been done mostly with people from Okinawa, even if now Anchor is actually in California, with both the experimental group of Shintake Sensei and the theory group of Nick Shannon, that many of you know here. And the second part of my talk is actually a collaboration with people in Germany, from the University of Augsburg, so both from the material chemistry and for the experimental physics part, and for the University of Munich for the theory part with Lode and Raja. So first, magnetic monopoles. So here, I don't know how much, I mean, everyone is quite familiar with frustration and with strongly correlated systems. And many of you are already familiar with spin-ice, but I will just give a brief overview about spin-ice and the interest of spin-ice before moving on to a more specific aspect. So spin-ice is now a young person. It's been discovered like 25 years ago with a renewal of interest 15 years ago with the magnetic monopoles. So spin-ice is realized, especially in solid-state physics, so in material like dysprosium titanate or holmium titanate and some related families. So what is the model of spin-ice? So here I'm going to first introduce you what is the physics of spin-ice. Spin-ice is on the power lattice, which is made of corner-sharing tetrahedra like this, with Ising spins at the corner of each tetrahedra, with And because they're Ising, they can take two different positions, pointing in or pointing outside. And you have 4 corner spins, which means 2 to the 4 equals 16 possible configurations. So these are the 16 possible states, with the ground state of spin ice being made of the configurations being 2 in and 2 out. Okay. So these states, these ground states, as you can see, for the magnetization is when you are in the ground state of spin ice, the magnetization is always conserved. So all the magnetization flux that enters the tetrahedron exits the tetrahedron. So it enters through the blue arrow and exits through the red ones. And it's the same for all of the states in the ground state. And because you have 6 different states in the ground state for one tetrahedron, when you pile up the whole lattice, the whole particle lattice, you get an extensive degeneracy, and you get residual entropy even in the ground state. So that's the core of the physics of spin ice, that it's strongly frustrated and highly degenerate. The ground state is highly degenerate with a measurable residual entropy at 0 temperature. It has been measured in these compounds. And so to describe the physics that's going on at very low temperature in spin ice, you can try to develop a field theory of these ground states. And this field theory is as follows. So as I said, the magnetization is conserved for each tetrahedron. And so it's conserved for all of the tetrahedron, for all of the system. And so locally, you can define a magnetic field B, effective magnetic field B, and its divergence is 0 because all of the flux that comes in goes out. And on top of that, you can write that the free energy is entropic in the ground state, and it's proportional to B squared. And with these 2 equations, you see that you have the Maxwell equation of a magnetic field B and the energy of magnetic field in vacuum. And so that's why the ground state of spin ice, described by these 6 states all over the lattice, all over the system, can be described as a Coulomb field theory of magnetostatic. Now, if you create excitations out of those, you create these 3 in, 1 out, 3 out, 1 in states. And these states can be seen as topological monopoles. So in the sense that they will locally break this divergence-free condition I was talking about before. So that means that the ground state can be seen as a Coulomb phase, as a magnetostatic, and the excited state can be seen as local charges, here topological or gauge charges of this gauge theory. Now, the magic of spin ice is that these spins are very big. They're Ising spins, and they have 10 Bohr magneton. 10 Bohr magneton, that's huge. That's some of the biggest single ion magnetic moment you can have in solid state physics. And so these Ising spins have strong dipolar interaction between them. And so if you remember your class from undergraduate, you can remember that when you have a positive and a negative charge next to each other, and if you look far away, the sum of these 2 Coulomb interactions gives you a dipolar interaction. So here we're going to do exactly the opposite. We have dipolar interactions coming from the spin. Each spin can be seen as a negative charge and a positive charge at the center of the neighboring tetrahedra. And so the dipolar interaction can be seen as a sum of 2 Coulomb potential from these magnetic charges here. That's called the dumbbell model that was shown, that was developed in this paper of Castelnuovo and collaborators in 2008. And so here in this case, you can see that you can revisit this context of ground state and excitation that I was talking about before. So in the ground state, you have 2 spins pointing in and 2 spins pointing out. You know, this flux of magnetization is conserved. Everything that enters goes out. And you can see that it corresponds indeed to 2 positive charge and 2 negative charge in the center of this tetrahedron here. And that means that in the ground state, you have magnetic neutrality in the tetrahedron. Now, if you flip one spin, you create an excitation. So here we were in the ground state. Now we flip one spin and we get into the excited state there. So you flip one spin here, and now you get 3 positive charge, blue ones, and 1 negative red charge. And so now you have an imbalance, and you have an overall positive magnetic charge in the center of this tetrahedron, which means that these excited states, which are gauge charges that we have been talking about before, which breaks this local divergence-free condition, on top of that, they carry effectively a magnetic charge in the middle. And so that's how you can rewrite the spin ice model with dipolar interactions in nearest neighbor interactions, nearest neighbor for magnetic interactions. You can rewrite it as a model with a chemical potential to create positive and negative charges and Coulomb interaction between these magnetic charges. So far, I hope that's okay. I've been going maybe a little bit fast on that. I suspect that many of you have already seen that. If you have any questions, please feel free to interrupt me.
Yeah. So let me ask you sort of a question, somewhat on my mind.
Sure.
Yeah. So what happens if you have octopolar interaction, whereas there's no dipolar interaction to this picture?
If you have, well, the octupolar one will. They will be on top of that. So you mean you will not have you don't have magnetic spins, but you have an octupolar moment?
Well, I mean, yeah, octopolar, yeah. Let's say you have no dipolar interaction, but instead octopolar interaction. I mean, as was claimed, right, by many people on the serum protocol, yeah.
Yeah, well, in this case, what you get is, well, in many instances, the octupolar interaction, the thing is the octupolar ones are decaying very, very fast. So actually what you consider is more the nearest neighbor exchange interactions you get between this pseudo moment. And then you consider the nearest neighbor physics, because the octupolar one will just disappear very, very quickly.
So I guess the question is, I mean, would you also expect some sort of a magnetic monopole? I mean, I guess not, right?
No, not from octupolar ones.
Okay.
I mean, not immediately. I mean, then what you can have is that from possibly in some model, from the nearest neighbor interaction you have between octupolar moment, you can maybe rewrite and think about emergent gauge charges. But the nature of the magnetic charge really comes from the fact that you have dipolar moment between the spins. So this monopole spin ice picture then, it looks like it can only be, correct for the this sort of a crystal lattice structure. For triangular lattice, I mean, do you have the same thing or you don't? Or for the triangular one?
Yeah.
So for triangular one, you will need to have some very, for triangular, I'm not saying it's impossible, but you will have to have some very fine-tuned model to have that. For Kagome, you have something similar. So you need an additional constraint, but you can have this spin ice physics in 2 dimension on the Kagome lattice.
Oh, so it's possible.
It's possible. It's just that you will be on Kagome, so your monopoles will be confined into a plane. But if the interaction comes from spins, then the dipolar interactions is 3-dimensional, which means that the Coulomb interaction between charges will also be 3-dimensional. And so even if you are confined into a plane, the nature of the Coulomb and the magnetostatic will still be, the interaction will still be 3-dimensional.
I see. Are there any claims by experiments? I mean, to people. I mean, I know people have claimed in the case of protocol lattice, the monopole excitations and so on and so forth. But are there claims in 2D materials?
So in 2D materials, you will have that in, for example, if you take the Parker lattice and you put a strong magnetic field in the 1-1-1 direction, you get a magnetization plateau. And so the magnetization plateau consists of 1/4 of the spins which are aligned along the magnetic field, and so they are frozen into the state. And the other 3/4 of spins form decoupled Kagome lattice. And these decoupled Kagome lattice have exactly the same divergence-free condition, zero divergence condition that you have here, which means that excitations out of these would create a magnetic monopoles. And actually, by further enhancing the magnetic field, you get a condensation of these magnetic charges.
Okay, yeah, thank you.
And in another example would be that in artificial spin ice. In artificial spin ice, it's expected that if you are on the Kagome symmetry, artificial spin ice, which is a spin ice with nanolithography, you can also expect the same kind of monopole magnetic charge physics.
Okay, yeah, thank you.
No, please, thank you for your question, and please feel free to continue to interrupt me. So this is a general picture of magnetic charges in pyrochlore, and now that's a classical picture. But now, if you add quantum fluctuations, you can define. If you have an effective magnetic field B, you can define an effective vector potential A, and if you have quantum fluctuations, that can be seen as kind of quantum dynamics. And these dynamics means that you can define a derivative with respect of time of the vector potential, and thus you can define an effective electric field, E. And so in this case, with the quantum dynamics, you get the magnetic field and the electric field, I mean effective magnetic and effective electric field, And so you recover the whole electromagnetism. And so in this case, you can have excitations in the form of photons. And these, so this paper is from Benton and collaborators from 2012, if I remember correctly. And so this linear, so this is energy omega as a function of wave vector k, and this linear dispersion here, this is the band structure that you can get from quantum spin ice, and this linear dispersion here corresponds to these photon excitations because omega equals k times c. So this slope is directly related to the effective speed of light that you get in quantum spin ice. And to conclude on this part, there have been some intense numerical work to study quantum spin ice, and some of the latest, not the latest, but some of the latest work of quantum Monte Carlo have shown that if you do simulations of quantum spin ice in quantum Monte Carlo, so the red squares are the specific heat, as you can see here on the y-axis, and the orange circles are the entropy. So it's just integrating the specific heat, okay? So when you are at high temperature, the entropy is R log 2 because you have a quantum spin S equal 1/2, so that's simply R log 2. Then as you decrease temperature, you have the first bump of classical spin ice, and then you enter into the classical spin ice regime in green here with a plateau of the entropy which corresponds to the plateau of classical spin ice. That's this residual entropy I was talking about here about this ground state. And then with quantum Monte Carlo, you can go to even lower temperatures, see a second bump of specific heat, and see this entropy disappearing and going to 0. And that's where you enter the quantum spin ice regime, which is not degenerate anymore, where you can see it as a kind of quantum superposition of all of the classical states in some hand waving.
Mm-hmm. So has this photons been seen by people? I mean, they're predicted by Nick Shannon and.
Yeah, so well, not only by Nick Shannon. I mean, there have been several papers, so including Nick and Owen, but there have been several people claiming and the photons. So theoretically, yes. I mean, field theory and yes, there have been some quite robust comparison between field theory and quantum simulations to also see these photons. Then experimentally, I'm not sure of the latest status of the observation of the photons. I think the photons are still at too low temperature. I mean, no, people are still more searching for like really quantum spin ice materials. So there are a few proposals. Then seeing photons is still difficult because it's really really low temperature. So I haven't checked the latest. I don't want to say anything wrong, but I'm not sure there is a conclusive signature of the photon.
Okay, thank you.
In experiments. So all of this is about magnetic monopoles, magnetic charges, and there have been several papers over the years in 2008 trying to measure this magnetic charge, and either with the dynamics, or with neutron scattering, or with mu-SR, or even with very high quality squid measurements, measuring the noise of these magnetic monopoles as they move in the sample. But the thing is, all of these measurements are indirect measurements. So they are consequences of the monopoles on the dynamics. They are measurements of the kind of Dirac strings you have monopoles and the correlations they create in the system. But it has not been possible so far to really see a magnetic monopole and to see the magnetic charge in experiments. So that's the question. What if we want to see not simply a crystal and see the consequence of a monopole in a crystal, but what if we actually want to see the magnetic charge inside the crystal? And so that's what we have been trying to do and over the past few years in Okinawa, especially with collaborators, and with electron holography. So first, I'm going to give you a very brief presentation of electron holography for theorists. Essentially, you get an electron beam coming from the top here, which is coherent. Then you use a lens to diverge this beam into two different beams. One of these two beams go through the sample, and so by going through the sample, the electron beam here gets a phase. I will go back to that one later. And then you recombine these beams together, and you use the biprism to have the different wavelength. I mean, to diffract it. And the point is, afterwards, you measure the hologram, which is essentially the interference pattern between the two beams. So that's really, in some sense, standard optical experiments, but with an electron beam here, that you see the interference and the hologram afterwards. Okay. So, and the point is, what happens if you have a monopole? So what happens if here in this sample, you have a magnetic charge? Well, the thing is, if you have a magnetic monopole, we have a vector potential A, and AZ is along the orthogonal, it's parallel to the electron beam, so it's orthogonal to the sample. And so in an electron going through the sample in the vicinity of the monopole will gain a phase phi through the Aharonov-Bohm effect, so equivalent to Aharonov-Bohm effect, gain a phase phi by simply being in the vicinity of this magnetic charge. And then, since you can measure this phase phi at the end, if you integrate the contour around singularity, around the magnetic charge, if you integrate this phase phi around this closed contour here, this is a singularity, and so this will take a finite value, which will correspond to the magnetic charge with the proper coefficient in front of it. So you see that with electron holography, with an electron beam going through it, you can go through all of, you can plan to see the phase shift due to the magnetic charge, and you can measure the magnetic charge of the monopole again.
Ludo, may I ask a quick question? So this would be correct if I'm not saying it's incorrect, sorry, maybe I should have phrased it differently. Anyway, I would totally believe what's on the slide. If the actual electrons were charged with respect to this capital A gauge field, right? But remember that this is technically an insulator, and this gauge field is introduced as a synthetic gauge field that appears as a result of representing spins in some pseudo-fermion notation. So I worry that the physical electron may not actually be charged. Like, you write minus E divided by H bar, that E implies that an electron is charged with that charge with respect to the electromagnetic field,
yes.
Right? And I worry that the A that you see is not the physical A, but sort of the synthetic gauge field, like in a quantum Hall effect, that has little to do with an actual physical field. Is that a consideration, or is that a worry?
No, well, that would be true if so the E here, that's really the E of the electron that goes that comes from the beam. So this E, the electron coming from the beam, does have an electric charge.
Of course, right. That's correct. But does it couple to A that in Michael Hermele's, way of looking at the loop of hexagon is some fictitious synthetic gauge field that comes from flipping charms? It has nothing to do with actual magnetic field, does it?
Well, that would be true if you didn't have these magnetic dipoles. So that's the thing that from here, from the point of view of the emergent gauge field, you are correct. If you only have the emergent gauge field, you will not have a real effective magnetic field, and so you will not have a real vector potential A. But the thing is here is that in spin ice and in the sample that we're going to talk about now, the gauge field, emergent gauge field, is the same, to a good approximation, is the same as the real magnetic field H in the system.
Oh, and that's because monopoles actually carry the magnetic spin, right? It's a 3-in, 1-out configuration, if you will.
Exactly. That's because the monopoles can really be seen as from the double model as a magnetic charge, and the other part of the magnetic charge creates this dipole with a real magnetic dipolar interaction. So the whole magnetic field comes from the fact that dipolar interactions really have a mu0 of 4 pi in front of them. And this mu0 of 4 pi reappears in the Coulomb potential between the magnetic monopoles. So
perfect. That makes sense.
So yeah.
Awesome, thanks.
And so just to be clear, divergence of B, so Maxwell equation is always correct. Divergence of B is always 0. It's just that for spin ice, divergence of M equals minus divergence of H. And so it's in the H field that you have the monopoles appearing. Okay. And so the thing is that you really have a real magnetic field, and so you really have a real vector potential A. So that's how from this vector potential you get the phase shift phi, and from the integration over a contour around a given point. So if you don't have any magnetic charge, this integration will give you 0. But if you have a magnetic, it should be. And if you have a magnetic charge, this integration will give you a finite value corresponding to the magnetic charge Qm here. And I should say that all of the experiments have been done by Anker in the group of Shintake Sensei with the help of Cathal, and he has also done many of the simulations and of the numerical calculation. So his thesis was really a mix of experiment and theory. So now, first we're going to benchmark our work with the previous work of Béchet and collaborators, which was published in Nature Physics 2014, where they did this experiment with a tip of a magnetized nickel sample. So you see you have a nickel, which is magnetized. You look at the really tip, very thin tip of that. And locally, this can be seen as a kind of North Pole here, and the South Pole being projected far away outside of the window of measurement. And so here we have done the experiments, which is the left panel here, and compare it to simulations, which is the middle panel here. And you can see that experiments and simulations, once you take the proper value of density of magnetic moment and so on, match very well to each other. The white part here being the needle, okay? So that's where the needle comes in. And so you can see that this is the phase shift that you can measure. And because this part looks like a magnetic charge, a magnetic charge, you have a phase shift as you circle around it. And so if you do the integration around this contour, around this phase, this magnetic charge, you see that you have a ramp of, you have a ramp of the value of the phase. If you integrate it, you can calculate the value of this magnetic charge here at the tip. Now, so this was done already in Béchet and collaborators. So here we just did that. We redid the experiment in our, so these are our experimental data and numerical data. We redid the experiment to benchmark it. But the thing is, with this kind of approach, you don't have a well-defined magnetic charge, because this radius here, if you increase the size of the radius, you will include more and more material, more and more magnetic moment. And by increasing more and more magnetic moment, you will increase the value of the magnetic charge. So the value of this magnetic charge here is not unique. It's dependent on the value of the radius, which means this magnetic charge is really a pseudo-magnetic charge, is ill-defined, and that's not a proper, that's really not a proper magnetic monopole. But still, it was still a very nice experiment done by Béchet and collaborators there. But
so what's the domain effect? I mean, the nickel is a ferromagnet, right? But ferromagnet is sort of a soft, right? There's many domains, right? How does that play a role in this?
So in this case, what you do is that you magnetize the sample beforehand. So you really put it in a strong magnetic field, just to be sure that it's really magnetized. And if you're at low enough temperature, it will stay in this magnetized state for long enough to do the experiments.
I see. Thank you.
Yeah. And so to comment on that, the additional thing that we did here in Okinawa compared to this initial paper is that we heated up the material. So we heated up nickel above its Curie temperature, so it became a paramagnet, and we could see that indeed this phase shift disappeared when we were beyond the Curie point. So we show that this phase shift is really coming from the magnetic moment of the nickel sample here, because when you heat it to make it paramagnet, it disappears. So this was our benchmark, and so now we wanted to move on to spin-ice systems to really try to measure magnetic monopoles. But the thing is, as we will see, doing it on solid-state spin-ice is not possible yet for technological reasons. And so we did it for artificial spin-ice. So artificial spin-ice, that's an analog of spin-ice grown by nanolithography. So it has been developed some like 15 years ago. And it's on a substrate. By nanolithography, you depose nanoislands of permalloy. Typically, it's permalloy. It can be something else, but typically it's permalloy. Nanoisland of permalloy here, and because they have this anisotropic shape, it's elongated. They can behave like local Ising moment, Ising degree of freedom. So locally, you have it's as if you have magnetic moment going this way or this way. So these nanoislands, they really behave like a local Ising degree of freedom, and if you look at them, locally, it looks like a Kagome lattice. So it is like simulating an Ising Kagome lattice in a 2D plane. So coming back to the question that I had at the beginning of this seminar. So we asked colleagues to grow this artificial spin ice, and then we measured the electron holography via TM, transverse electron microscopy. We measured it, and as you can see here, this is experimental data, and this is the theoretical curve. And we have a very good match between experimental phase map and the simulated phase map there. So it's the same thing as what I was showing before. You put the sample of spin ice in the TEM, in the transverse electron microscope. You measure you have a difference of phase map in one case. You recombine them, you measure the interference, and that's what gives you the experimental phase map that you have here that match very well with the simulated one if you assume this another length of permalloy. And now that we have that, we can draw a radius, because this is where the monopole, the magnetic charge, is at the center here. And so we can draw a radius around here, and we can integrate the value of this phase map as I was doing before. So here, this center, that corresponds to the center of the vertex. So in the same sense that spin ice, you have the magnetic charge at the center of the tetrahedron. Here you have it at the center of the vertex. So you have a magnetic charge at the center here, or possibly at the center here, and so on. So in this case, for this specific configuration, you have a magnetic charge at the center of this vertex that has been measured. And we have the experimental phase map. And so we can draw a radius. And as a function of the size of the radius, we can integrate what's inside and the magnetic charge that you have inside. And this is the curve that you have here. So the dots are the experimental data, and the solid line is the theoretical expectation from simulation. And you see that the integrated charge that you obtain increases linearly as you increase the radius. So that's the same thing that we have seen before with the tip of nickel. But at some point, for large enough radius, which are unfortunately outside of this window of measurement, experimental window of measurements, for large enough radius, we can check in simulations that this magnetic charge reaches a maximum, gets smoother, then it reaches a maximum, and then drops. That's because here, this system is a spin ice system. And so if your radius is roughly, which is the center of the nano-islands here, you are in this dumbbell model I was talking about before for spin ice, and you can locally define these magnetic charges in the same sense as for Pauclor before. And so this saturation here, that means that you have a well-defined magnetic charge in this at the center of this vertex. And in experiments, we could not go to large enough radius, but the match between experiments and simulations and the simulation tells us that we have this well-defined magnetic charge there. And just to confirm it, we did simulations with longer and longer nano-islands. So the same geometry of the lattice, but the nano-islands get thinner and thinner, which means that the vertices get further and further away. And as you do that, you see that the maximum is reached at longer and longer radius, and you reach, at some point, you reach a plateau, which corresponds to the theoretical expectation value of 3Q, because you have a free spins pointing in here. So inwards, inwards, and inwards, which means with the dumbbell model, it's as if you had free magnetic charge in the middle here. So you expect this 3Q vertex here. And that's the value you can reach if you have infinitely thin nano-islands there. So if I summarize, this is an artificial analog of spin ice system. You can locally create Ising spins pointing either inwards or outwards. If you look at the given vertex and you have 3 spins pointing in, from the dumbbell model I was talking about before, these 3 spins pointing in will all have a positive magnetic charge at the head of these. And this positive magnetic charge will give rise to singularity and to a given specific phase map with that experiments and simulations compare very well to each other. You can integrate around the contour of this phase to obtain the magnetic charge. Here again, experimental and simulation match very well. And you can see that in the proper regime, you can get a finite value of the magnetic charge here at this 3Q vertex, which means that you can measure an effective magnetic charge in artificial spin ice, and you can see it here. So this is essentially the vector potential of this magnetic charge that you can see here. Okay, so this is the idea for the artificial spin ice. Now, it's not possible yet to do these experiments on solid state spin ice for reasons of technical reasons I'm going to talk about later. But we did simulations to check how it would look like in spin ice. So what we did is we considered a thin film of power cloud spin ice. So this power cloud spin ice structure I was talking about before, we are going it as we are imagining that we have a thin film with like 4 layers of spin. So it's a very thin film. It's 1 cubic unit cell. It's 10 angstrom thickness. That's possible. It has been done. I mean, this is possible to do it experimentally. And what we do here is that we put a strong magnetic field in the plane of the thin film. So we polarize all of the magnetic moment along the magnetic field, so that all of the spin is pointing this way. And then we flip 1 spin here, and we continue to flip a chain of spins there, which correspond to this Dirac string between magnetic charges. So the point here is just, we start from a state where you have saturation, where you have 2 spins pointing in and 2 spins pointing out in all tetrahedra. So that's the ground state. And we artificially create an excitation, a magnetic charge there, a negative one. And the positive one, we move it step by step outside of the window of measurement. Okay. So here in this window, we only have 1 negative charge with 1 clear Dirac string. And you can see that if you simulate the electron microscopy measurements, you can measure the phase map. And this phase map is very similar to what we had before, with breaking, with a discontinuity of the phase map at the level of the Dirac string, but it starts negative, then goes up, goes up, goes up until it becomes positive there. And so that's what you can see here. And even if you have noise, even if you add numerical noise to simulate the noise of experiments, you can recover the value of the magnetic charge with this jump here. And so you can, and which correspond to the expected value that you can expect theoretically. So this is a simulated proof of concept that the same experiment can be done on a thin film of spin ice. And now how to measure monopoles, how to see monopoles in spin ice? Because the problem is that if you look at the phase map, this is what a phase map of a spin ice would look like in a thin film. And as you can see, these minus and plus charges are the magnetic charges, they are excitations. Everywhere else is in the ground state, so that's 2 in, 2 out, and the minus and plus are the magnetic charge. And as you move with time, like simulation time, Monte Carlo time, it represents like a real, to some extent represents like real dynamics. And as you move along with time, the magnetic charges move around, but even if they move around, you can see that it's very difficult to distinguish them from the background. Like if you only have, here in simulations, we know where they are, but if you only look at the phase map, it's nearly impossible to see where the magnetic charge are. So it's not very good to actually see the magnetic monopole. But so what you can do is you can measure the phase map at time t equals 0, and then at times t equal at different times, and you can subtract the two. So you can do a differential phase map here. And then if you do that, this differential phase map enhance all the changes you have between times t equals 0 and times t at 5 milliseconds, 10 milliseconds, 15 milliseconds. And so in this case, you can really see the movement of the monopoles. So here you see that the tip of the monopoles, the presence of the monopoles, are very clear in this phase map. And even if you add numerical noise to try to match experiments, try to represent experiments, you can still clearly see the discontinuity and the singularities there. Now, this is one aspect. So here it has shown that you can see monopoles as being the end of this Dirac string. So when a monopole moves, it leaves a wake of flip spin behind. These flip spins correspond to Dirac strings, and these Dirac strings correspond to a very sharp discontinuity of the phase map. And so when you look at the end of these Dirac strings, it corresponds to the monopoles that you can measure with this differential phase map. But now, the interesting thing that we noticed is what happens when you close these Dirac strings. And indeed, if we look at time t equal 20 milliseconds, between 15 and 20 milliseconds, there were some pairs of monopole created, hopping around and closing on themselves. And as you do that, locally, you create a jump of the phase map. And this jump of the phase map, this discontinuity, corresponds to fluctuations of this effective electric field that we were talking about before. So here in this case, it's an effective electric field. To come back to Andre's question at the beginning, the magnetic charge are present, but the emergent electric field is still to some extent artificial. So it's an effective one, but as you can see in electron holography, it will give rise to a discontinuity of the phase map, a very sharp one, very clear one, that can be measured in experiments. And so that means that both the Dirac strings, the magnetic charge, and the fluctuations of electric field could be measured with electron holography a priori. So now the question is, so this is a small video of what happens. So ideally, this is what you will be able to see in experiments. And now about technical requirements, cooling down the system to 700 millikelvin, because that's where you can see monopoles in spin ice. That should be possible. I mean, it has not been done, and it's not in any electron microscope, but there is no scientific difficulties for that. A spatial resolution of 350 picometers, that's what we need to be able to see these islands, these monopoles, and that's available with the best TEM machines in the world. A temporal resolution of 5 milliseconds at least, that's also possible, but a phase resolution of 0.4, 0.8 millirad, that's not there yet. Right now, I think the best microscope are more like around maybe 2 millirad, maybe it goes down to 1, but it's not there yet. So we still need to have one more technological step, that and include dilution fridge in the TEM to be able to realize experiments. But that's not an order of magnitude difference. That's something that is probably possible in the future. So with this, I end the first part of my seminar, and I'm already actually quite advanced. I will go fast for the second part. And so the second part of the seminar is about the centered paraclore lattice. So here I'm stepping a little bit away from spin ice and talking about frustrated magnetism in general. And as you know, frustrated magnetism is quite often made of elementary bricks of frustration. So the typical one is a triangle, like a triangular antiferromagnet. And when you combine these triangles locally in 2D or in 3 dimensions, you can get a whole variety of frustrated lattices, from triangular to kagome to hyperkagome and so on. Now you can also do the same thing with the tetrahedron in 3 dimensions. You can get a planar version of tetrahedron in 2D, but the natural tetrahedron is in 3 dimensions. And then when you make corner sharing tetrahedra, you get a paraclore lattice. But so the thing is, you see, when you have 3 nearest neighbor spin, you get a triangle, and you can pile that in 2 dimensions. That's triangular kagome lattices. When you get 4 spins at the same distance, you can get a tetrahedron, and you can get a paraclore lattice. But now, having 5 sides at the same distance, that's not possible in 3 dimensions, because you will need a 4th dimension to be able to have the 5 sides at the same distance from each other. But still, in chemistry, oh, sorry, I forgot to say. And these geometries, like for example, the kagome one and the paraclore one, as you can see from a quick Google Scholar search, there have been lots of intensive work on these different structures there. But the thing is, if you want to have 5 sites in a given frustrated unit, then you need to find some trick to be able to include the 5th site, because you cannot have it at the same distance, because in 3 dimension, in our 3D world, that's not possible. You cannot have 5 sites at the same distance in 3D. And so luckily, it is possible to do that by putting the 5th site at the center of a tetrahedron. And so that's this geometry that I'm going to talk about now. And so how to do that? You can do that with chemistry and with metal organics, metal azolites actually. So what we did is that we considered a manganese-based material. So why manganese? Because manganese is a 3D5 magnetic ion, and 3D5 means that half of the 3D band is filled. And half of the Philly band means that you have a large magnetic moment, so 5/2. That's very classical, so you can consider classical spins. And on top of that, because it's hard field, that's quite isotropic system. So you do not expect to have strong anisotropy here. You can, to a first approximation, you can really assume isotropic classical spins for manganese Mn2+ magnetic ion. And then between them, you put a ligand. So that's the whole chemistry part. And this ligand is this form here. With the metal ion, the manganese will be there, and it's connected by this different nitrogens ion. So if you look at the structure of MnTA2, so Ta is a triazolate. So if you look at the structure of this MnTA2, we did that down to 5 Kelvin for the whole range from 5 Kelvin to room temperature. And you can see that you have a nice FD3M cubic symmetry. And what is the symmetry of the system? This is the system that you get. So here it's difficult to see it. But if you zoom at one corner here, you can see that you have one manganese ion here in the middle, and you have the triazolate frameworks connected there. So the nitrogen 2 is connected to this one, and then the nitrogen 1 is connected to this. And you can see that the green manganese ions form a tetrahedron, and the red one is in the center of this tetrahedron here. So everywhere, the yellow octahedra correspond to this green manganese ions, and the red one here correspond to this green one here. So that's how you get a centered parallel lattice, where you have the green ones forming a parallel lattice, as we know and as we have already discussed before, and each tetrahedron has an additional manganese ion in the middle, forming this center, this new structure, this new geometry, this centered parallel structure. And for us physicists, we can really see this lattice this way. So with a parallel lattice and with the centered ion in the middle. And ab initio DFT calculation tells us that J1 and J2 are of the same order of magnitude, while J3 is much smaller because J3 does not have the nice nitrogen connection between them. Okay. And so you can see that J1 and J2 are the same order because J1 is between, you go through N2 and N1, while J2, you go through N1, N2, and N1. So it's just adding one more nitrogen difference between J1 and J2 coupling. So that's why they are of the same order of magnitude. And so that's why the Hamiltonian we're going to consider is this centered parallel lattice with J1 interactions between the center spin and the corner spins, and J2 interactions between the corner spins. So here, if it was just J2, it would be a parallel lattice. If it was just J1, it would be a decorated diamond lattice. But with J1 and J2, we have this strongly frustrated geometry that we're going to study now. And the important fact is that if you do experiments, like if you measure the susceptibility of this material, MnTA2, this is the black dots are experimental data. And if you fit the high temperature with the Curie-Weiss law, you get a Curie-Weiss temperature of -21 Kelvin and a magnetic moment of around 6 Bohr magneton, which correspond to the spin S equal 5/2 that I was talking about before. And this is consistent with one of the only paper on this material that was a chemistry paper that was published in 2012. And now if you measure the specific heat, you see that you have a phase transition at 0.43 Kelvin, which means that the Curie-Weiss temperature divided by the transition temperature gives you a frustration index of roughly 50. So this is a general experimental measurement of the strength of frustration. And the value of 50, that's a highly frustrated magnet. That's much bigger than 1. And that's noticeably more than most pyrochlore and of the same order as K-type materials. So this MnTA2 material has a strong frustration index. And because Curie-Weiss temperature tells you the strength of the nearest neighbor interactions, and TC gives you the value of the transition, which means that you will expect a transition at this value, but you only get it at this value. And so this ratio tells you it's a very highly frustrated system. And then we have compared the susceptibility, so it's Chi temperature here. We have compared the susceptibility and the magnetization in the magnetic field with Monte Carlo simulations. And so we use Monte Carlo because, as we discussed before, we have this nice J1, J2 Hamiltonian, and we have manganese ions which have strong magnetic moment, and are isotropic. So you can use classical Heisenberg spins there. And when we compared simulations to experiments, both in the field or in the susceptibility, we find a very good agreement down to roughly 1 Kelvin or a little bit below for a value of eta. So eta is J2 divided by J1. That's the ratio of the two interaction matrix of roughly 0.67. And this value of 0.67 compares very well with DFT estimate of 0.69. So both magnetic measurements compared to simulations and DFT ab initio calculations give us the same ratio of J2 over J1 for this material of MNTA2. And in addition, we try to calculate the specific heat. So we cannot use classical Monte Carlo for specific heat because the entropy is ill-defined in continuous classical spins. So we cannot calculate the specific heat properly. So we did a very rough approximation with exact generalization. So it's a non-controlled approximation. But with playing with J1 and J2, we could estimate the value of eta, and we found something of the order of 0.6 actually, 0.57, 0.6, which reproduces this bump here of the specific heat.
What is TC here? I'm sorry, what is TC? I mean, I'm still confused.
TC is the transition temperature. So the system at low temperature at 430 millikelvin orders into a long-range ordered state.
Okay. So what kind of magnetic structure orders to?
We don't know, because the problem is that it's an organic material, so there are hydrogen ions, and hydrogens absorb neutrons, which means you cannot use the usual neutron scattering to probe the magnetic structure. So it needs more work to be able to pinpoint the nature of this magnetic order. Okay.
And Ludovic, I missed it. What is your definition of eta? Sorry, is that some coefficient of the fitting?
Yeah, it's J2. I'm sorry, I should have written it before. It's J2 divided by J1.
Oh, I see. Okay. Thank you.
So you see, J2 is between corner spins. J1 is between central and corner spins. So J1 is a strong one. J2 is a little bit smaller. And eta is J2 over J1. I'm sorry, I should have written it.
Okay, thanks.
So it's just, essentially, since you have a model with only two parameters, the ratio of the two is the characteristic parameter that will describe the physics of the model. And so this value of eta in ab initio calculations and in Monte Carlo simulation compared to magnetic measurements give us roughly the same value. And if we do some rough exact generalization approximation to model this bump, we also find a similar value approximate of 0.6. So, and this bump here, that's essentially the onset of quantum correlations. That was also observed in ytterbium titanate in many power core systems. You have a bump at a few Kelvin, and this bump corresponds to the onset of quantum correlations at the level of 1 tetrahedron. So above this bump, that's essentially paramagnetism, and below this bump, that's the onset of quantum fluctuations.
Well, why would you expect quantum fluctuation to be at such a large temperature when you have a classical spin? I mean, 5.5.
It's just because the classical spins, the continuous classical spins, cannot reproduce the specific heat properly, because the classical fluctuations being continuous, you cannot reproduce the entropy, and so you cannot reproduce the specific heat. So if you want to compare things below this bump, you need to include the discreteness of quantum mechanics. So that in that sense, it's in that sense that it is that the quantum mechanics kicks in.
But I thought based on what you plotted here, I mean, the system is actually in the paramagnetic state, right? I mean, if it was very strong electron correlations, in the paramagnetic state, I mean, the magnetism can contribute into heat capacity as well, right? I mean, since you don't really know what happens at the 0.43 Kelvin, what sort of magnetic phase transition it is, yeah. So I'm puzzled, yeah.
So this one is not a phase transition; it's just a bump, so it's a crossover.
I know, it's not a phase transition, yeah. But I mean, when you have spin fluctuations, when you have a very strong, magnetic order, even in the paramagnetic state, you can have a, very strong spin correlations, right? The strong spin correlations, may have a very strong temperature, may have strong temperature dependence that can contribute, to your. I mean, it's hard for me to believe, with a spin of a 5.5, you have such a quantum effect.
So I'm I should rephrase. I should be more careful with what I said. I mean, it's we are still expecting classical physics here. I'm sorry, I was not clear enough. We're still expecting classical physics here. It is a classical system indeed with a spin s equal 5r. It's classical. It's just that this part here and the specific heat going down cannot be described by continuous classical spins. You need to consider discretization to be able to see that, because continuous spins have an ill-defined entropy and specific heat at low temperature. So that's a problem of classical spins more than the material itself. But so once you induce a bit of this discretization here, that's what we have done there, you can recover this bump here. So it's not, to correct what I just said, it's not so much quantum coherence that appears, it's just that you need this discretization of the spin s equal 5/2 to be able to model and to understand this bump here in specific heat.
So this bump here in specific heat, I mean, so it's purely driven by magnetic frustration, or it's driven by, yes. There's no electronic contribution, right? Because it's insulated, right? So it has to be. So there's also, I mean, are there any lattice change around this temperature? I mean, the temperature is high enough, right, to have a lattice change, right?
We have measured. So this part here is actually the magnetic contribution of specific heat, because of course they measure the whole specific heat, but they have measured also the specific heat for the non-magnetic sample, non-magnetic equivalent, and by subtracting the two with the correct Jaubert coefficient, you can get rid of the phonon and lattice contribution, and you can just get the magnetic one. So this one is just the magnetic one.
Thank you.
So this one is indeed essentially the onset of magnetic correlations.
Okay, thank you.
Okay. Yeah. No, thank you. And so what it means is that we have parameterization of manganese parameters in this region of the phase diagram. We have a phase transition at Tc, which is not in our model, because you see that in this region of the phase diagram, when you do classical Monte Carlo simulations, we do not find any phase transition. So this phase transition at Tc is beyond our model, so we need to introduce other terms to understand it. But our point is that at this intermediate temperature above Tc, we expect to have a regime of temperature where we can see the proximity of this spin liquid system. So for manganese MNTA2 parameters, classical Monte Carlo simulations find no long range order. In experiments, we have it at very low temperature, so we cannot describe the very low temperature physics of MNTA2, but at intermediate temperature here, and so in experiments that will correspond to this temperature regime or this temperature regime here, in this temperature regime here, we can expect to see the proximity of a spin liquid state in MNTA2. So this regime here will correspond to a classical spin liquid. And I think I've already been quite, it would taken quite some time. So I think I will move fast for this one. Just the phase diagram that we get from classical Monte Carlo, as we move the ratio between J2 and J1, so eta is J2 over J1, okay? As we move the ratio between 0 and 1, we get from a ferrimagnet, where the central spin is opposed to all of the other spins, to a partial ferrimagnet and to a spin liquid regime. So that's what we can get from at 0 temperature exactly, and at finite temperature for Monte Carlo simulations. And if you measure structure factor, you can see pinch points of 3D isomagnetic magnet at large value of eta, and these pinch points become more and more diffuse. And I'm not going to go into the details here. I don't have time. But essentially, we can understand this diffuse pinch point that we see in structure factor as being the fluctuations of this central spin in the centered particle lattice. And so this is my conclusion. On one side, the first part, we could show you how magnetic charge, magnetic monopoles could be observed in electron holography. So this was done in artificial spin ice, and we have shown how to do it in a thin film of a power spin ice. And we have also shown you a new geometry of the centered particle lattice, with which is the first really joint theory experiment calculation and measurements on this material. And we have shown that the finite temperature properties around 1 Kelvin and above can be well mapped with a simple J1, J2 model. and which is a proximity of a spin liquid phase. So thank you very much.
Thanks, Ludovic. So we do have time for a couple of questions. So using my prerogative as a chair, could you go back one slide and tell us about this fourth emergent dimension? How should I think about this? Yeah, right there. You say it on a slide, but I could you tell us the punchline? Like, how should I think about this fourth dimension?
Yeah, so the fourth dimension, actually, so I didn't know that, but the Schlegel diagram, that's a way to represent a 4D in a 3D space. And actually, a pentacore, that's 5 sites at equidistant from each other in 4 dimensions. And if the representation of a pentacoron in 3D in the Schlegel diagram, that's exactly a centered tetrahedron like this. And so the way to understand it is if we go one dimension below, so that's things that we discussed previously, but if you go 1 dimension below and you consider the 2D centered Kagome lattice with a Kagome lattice like this, which are the black dot and the centered spin, which is a red one, you can see it as a slab of a parallel lattice. So if you take this spin, you make it up, that would be this, and you take this one and you put it down, that would be this one and this one, and alternatively up and above and below the Kagome lattice. This is exactly a slab of a parallel system. And we can show, I mean, this is known for a long time, and this is a figure from Zitomeski from 2008. On the Kagome lattice, you have sharp pinch points, so that can get even sharper than that. But if you do simulations of this 3D parallel slab, so with the Kagome and with this additional spin up there and there, these pinch points become diffuse, broad and diffused pinch point there. That's because even if you still have the Heisenberg antiferromagnetic physics as the Kagome, so you still have that, but these spins here are they are not connected to another tetrahedron above or another tetrahedron below, and because of that, there are 3 spins, and over there the magnetization flux was talking about. Here it can go out of the system there and re-enter somewhere else. So this divergence free condition I was talking about, it's not constrained within the system, within the 2D plane or the 3D slab. It can exit the system through this extra dimension. And that this exiting of the magnetization flux, that creates diffuse pinch points, because these pinch points really come from the 0 divergence condition locally. And because you lose that, that's why you get diffuse pinch points. And so if you do sharp pinch points, but in our centered parallel lattice, which corresponds to a slab of this 4D1, you get only diffuse pinch points there. So with a good comparison between analytics and Monte Carlo simulations.
I see. So you could basically look at this metallographic system as sort of a slab, like a 3-dimensional cross-section slab of a 4-dimensional lattice.
Yes, exactly. So it's knowing that so here the point is that the center spin will be alternatively, on A and B tetrahedra, the center spin will be moved along plus T on the 4th dimension and minus T on the for the neighboring tetrahedron. So in the same alternative way you have there. And if you do that, you have really a 3D slab, which is very, very thin along the 4th dimension. And so that's why here the Fourier transform is actually on a 4-dimensional space, but you cannot access the 4th dimension because it's a very thin slab, so you can you don't have enough thickness to access Fourier space there.
Mm-hmm. Great, thanks for that. Yeah.
So yeah, I'm still puzzled by so you have this very large spin system, yet you're suggesting that there's some sort of a quantum spin liquid phase. I mean, are you expecting fractionalized excitations? I mean, of these? So I mean, I don't think there's any claim, right, of a quantum spin liquid for such a classical system, right?
No, I agree, and I should apologize because I was not careful enough in my wording. So you are right. Here we do not. So here that's this regime here. In this regime, we still expect things to be classical. It's S = 5/2, so we still expect things to be classical here. So this region is a region of moderately strong correlations. So
okay.
this is really
So
the paramagnet.
basically, it's coming from spin fluctuation due to geometry, right? I mean, may
Exactly.
have nothing to do with fractionized excitation, the quantum entanglement people claim
No.
in the spin of a half system.
No, I do not expect quantum fractionalization, and I do not expect quantum entanglement, or at least nothing strong, nothing major there, because for this spin S quadrat. But all I wanted to say is just that to model this deeper specific heat, we needed to introduce discretization by hand, but we can still do that in a classical way, sort of.
So Andre, so this is sort of similar to our nickel 238 system, right? We have a spin 1. We claim to see fraction, continuum, right? The referee complains saying that are we claiming fractionization? We're not, right? Yeah.
Right. Well, so I guess maybe one way to ask this question. So Ludovic, imagine you're studying a classical spin ice with dysprosium, right, or holmium. Nobody would argue that the spin is huge, right? 10 Bohr magnetons, so for all purposes is classical.
Sure.
But if you look at the inelastic neutrons, which of course very hard to do, right, at those low temperatures, but let's say you did them, right? In that particular case, my understanding is that you wouldn't see any diffuse scattering, right? And that just presumably due to what? That the spin ice rule disobeying transitions, that they just cost too little energy. Like you would need neutrons at very, very high resolution to see that in energy. What I'm trying to ask, sorry, it's an ill-posed question perhaps, is the following. How would you distinguish a quantum spin liquid, of which often people say the hallmark is a diffuse scattering in energy or momentum, versus a classical spin liquid such as holmium dysprosium titanate? Can you use the fact that you don't see this diffuse scattering as it's a statement that it's classical, not quantum, or is it deeper than that?
Okay, so to answer the first part of the question, my naive approach is that usually the quantum spin liquids they usually lose the classical degeneracy, the degeneracy of the classical system, the classical spin liquid.
That's right.
Which means that if you measure, for example, in spin ice, there have been some debate, but the latest experimental data show that you have residual entropy in dysprosium and holmium, and this residual entropy corresponds to the classical degeneracy of the system. So that's why, at least for these temperatures, we expect to have classical physics.
Okay, so you haven't yet reached the temperatures where any quantum effect might play a role. Would probably be fair to say.
I would not say any quantum effect matters, but I would say it's still dominated by classical physics, because you can have, because the thing is, dysprosium, the single ion physics of dysprosium, you have a gap, it's a big gap, but you have a gap to the highest excited state for single ion. And this gap, when you reach low enough temperature, you may be able to see in front of this gap on the dynamics, like of the spins. And so it is possible that part of the dynamics of dysprosium or holmium material at very low temperature might have some quantum influence in there, like some, I don't know, transverse field or something like this. So that's not impossible, even if that's not impossible. But then to come back to your point about the, that's a good question, and to be honest, I will need to think more carefully to give a proper answer. I don't want to say anything wrong.
Do people see lattice distortion at the magnetic phase transition? I mean, I know you cannot do neutron scattering, but I mean, X-ray scattering can potentially be done, right? I mean, do people see any structural changes at the position where you see, heat capacity anomaly and also the magnetic phase transition?
So we did XRD down to a pretty low temperature, down to 5 Kelvin, and we don't see, and we also did some other experiments down to very low temperature, and we don't see any indication of lattice distortion in this material, which is not the case in other metal isolates. So that's the thing, that this material, because of the very strong isotropy of manganese, you really seem to conserve this cubic symmetry. Maybe at very low, I mean, this cubic symmetry, as far as we can tell, is really there. While in other materials, other metal isolates, this cubic symmetry seem to sometimes split and becomes tetragonal, and then you get a slightly more complicated Hamiltonian. But here, as far as we're concerned, we don't see any lattice distortion. I mean,
Yeah, so within the error, within the error of the X-ray measurement. Yeah, okay.
Yeah, exactly. Yeah.
So given the lateness of time, maybe we should pause here. So before I pause the recording, Ludovic, thanks again for the wonderful talk. And if people want to stay and ask questions informally, you may. I just want to make sure that we don't keep people here on purpose.
Thank you very much. Very nice talk.